So earlier it was here. Now it will try to align with B, and the next step it will try to align with C. So in this case, this is how brushless DC motor works. Now, how do we know that when to turn on and off these A, B and C magnets? So for that, we have three Hall effect sensors. H1, H2 and H3. So by the combinations of H1, H2, H3, we can detect the position of the rotor. So H1, H2 and H3 can be the combinations of 1 and 0. So it can be 1 0 0, 1 1 0, 1 1 1, 1 0 0 or whatever. So this is how we detect the position of the rotor, and these Hall effect sensors serve as a feedback to the operation, that how we are going to turn on and off these magnets. And it doesn't matter how fast or slow we go, we have a feedback to turn on and off the motors or magnets, and that's how we can operate our brushless DC motors. Now these A, B and C coils can be connected in star configuration or the delta configuration. So this is the delta or Y configuration, and this is the star configuration. So A, B, C, A, B, C, and if we turn on, these are the nodes. So if we disconnect the node 3, we will have a rotation current movement from 1 through 1 to 2. Sorry. So 3 is disconnected, rotation from 1 to 2, and coil A is engaged. If you disengage number 1, so you have a rotation from 2 to 3, and coil C is engaged. Then you disconnect 2, and you will have a rotation current movement from 3 to 1, which says your coil B will be engaged. However, if we move to the star configuration, if number 3 is disconnected, so you have a current movement from node 1 to node 2, your coil A and B are engaged. So if you disconnect number 1, so it will be from 2 to 3, and the engaged coils will be B and C. And if we disconnect number 2, so there will be a movement from 1 to 3 and or 3 to 1, sorry, and coil C and A will be engaged. So these are the two kind of configuration in the brushless DC motor. I started with a discussion of 3 coils, and these 3 coils can be connected in either of these configurations. And there are always limitations and advantages associated with each of the configuration. When we start the motor, we prefer it to be in the Y configuration or the star configuration, and when the motor is running, we prefer it to be in the delta or Y. It's delta configuration. So why do we prefer it to start in this configuration, and when it is running to switch to this configuration? There is a reason for that. We can see here the voltage drop is across the 2 coils instead of having 1. So magnetic field is distributed, and when we turn on the magnet, or when we turn on the motor, so this is our stator and this is our rotor. It has its on north south, and this guy has its on north south, and those fields are not aligned. At the beginning of the rotation, their fields are not aligned, and the non-alignment will cause a back EMF induced to the rotor, and because of that, heat will be produced up, and we have a chance that our rotor or stator or the whole motor can be burned. And to avoid that, we distribute the voltage drop across the 2 magnets. However, this will not give us the maximum speed. So when is it in the running condition, we can use some sort of relays to disconnect it from the Y configuration and push it towards the delta configuration. And in this case, we can see only 1 coil is engaged, so we get a better torque and better speed. So that's why we prefer the delta configuration. And also I would like to cover up one more topic. That's if I disconnect the node 2, how there is a rotation between 1 and 2, or if I disconnect node 2, how the rotation, how only this coil is engaged, why the current is not flowing from here to here. Because we use 3 half bridges connected to, I described the concept of edge bridge, and we use 3 of those half edge bridges on each coil, and we can disconnect and connect each and every coil as per our choice. So this is all about the motors. Now for the experiment we are going to do, we need to fill out a table. And for that table we need a phasor diagram. Based on the rotation or the position of the rotor or what the Hall effect sensors are reading, we have 001 for the Hall effect sensor here, 001, that's 011, 101, 100, 110, 010. And in between we have A as, okay, I'm not gonna write the ABC, I will just write the A minus and 0. So this guy over here is plus 0 and minus. Over here is 0 plus minus. Here minus plus 0 minus 0 plus 0 minus plus. So whatever our Hall effect sensor is reading, we just have to go 90-degree clockwise to find out the position, a relative position of the so we go 90-degree clockwise and we get to know the value of A, B and C. So that's high, that's 0 and low. Let's look at other one. So if we consider this guy, that's over here, 0, high and low. So we have to fill out this table, and based on this table our motor is going to rotate. If motor doesn't have a logic, it is not going to rotate, and that is expected from you to fill out the table so that we can have a motor running. Otherwise we cannot have a motor running if you don't fill it out. So next motor is stepper motor. So for the purposes of this lab, we will be using a unipolar motor, and I will be demonstrating a very basic model of a stepper motor with a 4 coils. So this is A, B, C and D. We have 4 coils. B, C and D. And this is our rotor and this is our stator. This is very similar to what we covered in the brushless DC motor. However, here we have to go in steps instead of having a full rotation, and we are not using Hall effect sensors. We don't have any kind of feedback in the stepper motors. However, if you want to incorporate some sort of feedback, you are more than happy to do that. But for this experiment, we are not going to do that. So I would demonstrate a very basic model where we will start with a wave drive, simplest of all. We have 4 magnets, A, B, C and D. So in the first step, I will turn on A and rest all are off. So this rotor will try to align with the coil A. In the next step, I will turn off A and I will turn on B. So for instance, if it was here earlier, it will be pushed towards that side. In the third configuration, I will turn on C and the rotor will be pushed to that direction. Fourth configuration, I will turn on D and the rotor will go towards that direction. So here we can see we have a continuous rotation, and that too in steps, not the continuous rotation without any feedback. And if we move to the next kind of drive, that is full step drive, so here I turn on 1 and 2 or A and B simultaneously instead of just going with one. In the second step, so in the first step, if I turn on both A and B, it will neither be aligned with A or B. However, it will align in a direction in between of those two coils. In the next step, I turn on B and C and turn A off. So it will be pushed towards this direction. Here. In the next step, it will be these two, and in the last step, it will be these two. Now after studying the full step, next is the half step drive. In the half step, what we do is, first we turn on this A and B. So my motor or my rotor is aligned in between the A and B. In the next step, I will turn A off and I will keep on turning B. So from here, I will move towards this step. So if B is on, so this will be 0, 1, 0, 0. All the rest of all the coils are off. Only B is on. In the next step, I keep the B on, and I turn on the C. And in the next step, I go here. So here I can see that half step drive is the combination of full step drive and the wave drive, and we get half steps instead of getting the whole one step rotation. We are getting half step rotation. Now how do we get number of degrees on per steps? So it's very important to calculate number of degrees per step. For instance, if this is my rotor, and if now my rotor will also have some teeth. So 1, 2, 3, 4, 5. The experiment we will be covering has 6 teeth. So I'm going to delete this. How to calculate the number of degrees per step? So number of teeth equals, here I have 5 but I'm going with 6 because we have 6 in our setup, and number of coils is 4, so number of steps will be 6 into 4, that's 24. If you want to calculate degrees per step, degrees per step, so it's 360 divided by 24, that will be around 50. So this is the degrees per step, and the degrees for half step will be around 7.5 degrees. And after covering all this material, I'm going to cover something more. That's the, it will not be demonstrated in the experiment, but I'm going over the theory of micro stepping. In the half step drive, wave drive, and full step drive, we were using digital pulses, but instead of using digital pulses, we can also use analog pulses. So instead of making A as high, we can make A as a sine wave, B as a sine wave, C as a sine wave. These are the half sine waves, so, and D as a sine wave. So here in this configuration, we can see that instead of going for whole step or half step, we can achieve a fraction of a step, and we can control these sine waves because these are the analog signals. We are able to achieve very good precision and accuracy with these, and that's why we are able to use it in the 3D printers. That's the main application of stepper motor. We can also use it in the rack and pinion, robots, etc., etc. So now the last type of motor, or the actuators, that I am going to cover is the servo motor. Servo motor basically works on a PWM signal that we already discussed and covered in the previous discussions. So basically if you have a servo motor, so if duty is 100%, this is going to turn its full rotation. I'm just considering it to be 30, whatever the limit of servo is, I don't know, but I'm just assuming a number. for instance, this is a full rotation of the servo. So for the 100% duty cycle, it is going to rotate full rotation, and for the duty cycle of 0%, it will go for the same full rotation in the opposite direction. And if we have a duty cycle of 50%, it will be at 0 degree. So this is known as the neutral pulse. This is known as high pulse, this is known as low pulse, and this is known as neutral pulse. If we have a duty cycle in between 50 and 100, then our motor is going to rest somewhere in between, depending upon the rotation we want. So it is a full feedback system, and we just have to provide the number of degrees it has to rotate, and it goes to that position. And I would say that for our experiment, you guys need to find a calibration factor, because you will be providing a voltage signal, and with respect to the voltage signal, it is going to go over that position. Now you have to find a calibration factor which will give you, which will help you transform from the PWM signal to theta. So software we are using is LabVIEW, and in the LabVIEW you have to tell a PWM signal, and it goes to a particular theta. Now I need to find a gain. So what is the gain? So gain is when gain is being multiplied by PWM, this means theta. So gain is theta, which is in degrees, divided by the PWM, which will be in the volts. So it will. So we need to find a gain, which will be degree per volts. I'm sorry, I think I'm mistaken over here. So instead of volts, it's milliseconds here. So this is a pulse. What is the count in millisecond of the pulse, and what's the theta with respect to it? So degrees per millisecond as a gain that we need to find, and we need to plug that in the software to calibrate our motor, and it can perform the desired operation. And if we talk about the applications of servo, we can see it all the way around. Mostly it's used in the robotic arms, or wherever constrained or fixed motion is desired. For instance, if we need to go from 0 degree to 90 degree and come back to 0 degree, similar operations like that. But if we need a continuous rotations, then we use steppers instead, because servos are limited by a certain number. It cannot go beyond that particular range, and we have to consider it before implementing it in the hardware. So these are all different kind of actuators, and it's our choice. We can use any kind of actuator based on the application we need. That's the most important point to consider actuator. So this is all for this experiment, and I hope you can perform these experiments after watching this video. Thank you very much, everyone.